Okay. So this is how to get, and this is just two-dimensional. So this is sort of interesting because it's even two-dimensional. It's already really interesting, really complicated, difficult to understand. And actually, there's a picture of Plato meeting Napoleon, and it's funny because I read that Napoleon was a big fan, but in the picture he looks pretty mad. Like slightly displeased. Yeah. So I'm very proud of this picture. And so the question is, why do you need to understand them? And the real answer is the eigenfunctions of the Laplacian, and the Laplacian is one of the basic objects in the mathematical universe. That's one way of saying it. You understand the Schrödinger equation, heat equation, wave equation, anything like this. You're going to need the Laplacian, and as always, if you're going to operate it, you're going to diagonalize, right? Here's another interesting way of thinking about Laplacian eigenfunctions. So I claim this to be the first inverse spectral theorem in existence. So this is from Erasmus Darwin, who was Charles's grandfather. And he tells a story of someone entering his office who's blind and deducing from the reverberations in the room the dimensions of the room. Yeah, it's pretty nice. Erasmus is well worth a visit to Wikipedia, a very interesting character himself. Okay, I'll start in the very beginning. In the very beginning, meaning my chronological beginning. And it's going to be disconnected and then it's going to be connected. Okay? Because the story for me started 8 years ago, time flies. So I was working with two friends of mine. This is Diogo Oliveira, Gaspar Teixeira e Silva. I practiced. And Felipe Gonçalves. I'm being recorded, right? So the amount of stories I can tell are limited. Ask me afterwards. So in 2015, we're looking at a harmonic analysis problem, which was raised by Bourgain, Clausel, and Kahan, maybe in 2008, 2009. We're looking at this stuff. And at some point, we needed a very curious result. And it was very precise, and we needed it as a lemma in the proof. What we needed was a statement about Hamid functions. So Hamid functions are, in case you've never seen them, there are family of functions on the real line that index by an integer. And the first one's a Gaussian, who then is oscillating more and more, and they have a large number of wonderful properties. In particular, the eigenfunctions of this operator. The other reason why we needed this in Fourier analysis is the eigenfunctions of the Fourier transform that are pretty nice. And the statement that we needed was very, very explicit. What we needed is the following. If you pick any finite set of numbers on the real line, you can always find an infinite number of Hamid functions that are all positive in those points. So, you give me 27 points on the real line, and I can use infinite number of Hamid functions whose index is a multiple of 4, which is explained by the previous slide. I to the 4 is 1. So it's always possible. And what's funny about the result is, it's not a priori clear that it's true, because if you are doing the following, if you look at the numbers 1, 2, 3, and 4, and you're trying to find a Hamid function that's positive in 1, positive in 2, negative in 3, positive in 4, there's only finitely many. In fact, there aren't any, but we didn't prove it because it wasn't needed. We proved there are finitely many, just to show that this type of result is sort of interesting in its own right. So it's an interesting pattern. And the proof is very, very simple. You can give it on one slide. We pick a finite number of real numbers, look at the compact interval, and it turns out on compact intervals, as n becomes large, these Hamid functions become fairly regular, which to people who do quantum mechanics is known as a WQP expansion. So they become fairly regular, right? And really, that's just a cosine. Okay, so what we're looking at, morally speaking, up to small errors, is we're really looking at this sequence of points in the m-dimensional torus. Because the cosine is 2 pi periodic, right? I don't care what this number is. I care what this number is marginal 2 pi. So suddenly I'm on the m-dimensional torus, and I've got a sequence of points. And that looks sort of complicated, but then you think, okay, n is really, really large. If n is really, really large, the difference between square root n and square root n plus 1 is really tiny. So really, it's not a sequence of points. It's almost like a sequence of points degenerating into a line. So really, you need to understand lines in the torus, right? Not so bad. And it turns out, if I look at a linear flow, which this thing is sort of discretizing very nicely, a linear flow in the torus that gets goes through the origin will get arbitrarily close again and again. This is just the Poincare recurrence theorem. And if you were to go into the theory of numbers, the geometry of numbers, you could make it quantitative. We don't need this. So you're going to find large P where this is very close to the origin. The cosine is positive to the origin. We're done. Okay. But this kind of really thinking and said, okay, what's the general theory like, right? So suppose we have a nice potential, and I'm not going to define what nice is. Suppose we have a nice potential on the real line, and we look at solutions of this ordinary differential equation. What can we say? In particular, if I pick 2 points on the real line, and I start looking at eigenfunctions of this equation, or solutions of the ODE, is there any correlation in the sign of the solution at those 2 points? And if I look at it, it's an infinite family of functions, after values at 5 and 7 connected. Do they talk to each other? And the first thought that you might have is, of course, not. The way I'm just introducing this one. I'm just counting among the first n solutions, how many of those have the same sign in x and y. You'd expect them to be roughly 50%, right? Because these values could be uncorrelated, they could be sort of random, there should be no connection. That would be the first gut instinct. The second gut instinct is, well, we're looking at sort of a one-dimensional Schrödinger equation, right? There's only left and right because it's one-dimensional. So there's a lot of rigidity in it, right? The waves can only go left and right. So maybe there is some connection. And what we were able to prove that in a reasonable sense, most points are completely decorrelated. But there's an extreme set that is slightly correlated or slightly positively or negatively correlated. So it turns out you can actually find points under reasonable assumptions, which I'm not defining, where there is some connection. Meaning, even though they're distinct points far away from each other, and we're looking at sort of high frequency waves, nonetheless, the value here, they talk to each other. I'll give you an explicit example, which is for the Hermite functions we've just seen. If you look at the points 0.5 and 2.5, you can actually compute that in the limit, they agree 60% of the time in sign. So the points 0.5 and 2.5 are actually connected. And you can actually, it's an asymptotic result, but it's pretty concrete as well. If you look at the first 1,000 numbers, you see that 603 times the sign is actually the same. Okay. So what does this have to do with Laplacian eigenfunctions? Well, these are Laplacian eigenfunctions, but that's not the ones we're sort of interested in, maybe. So, outline for the rest of the talk. Basic question about any function is how big is it? How big can it be? And that's the question we'll ask you as well. In particular, as you have more, sines and cosines or spherical harmonics, sometimes you see they can be more concentrated. How concentrated can they be? How does the dependence of function on k for the eigenvalue? And then I'm going to type of the analogous thing. I'm going to say, is there any way to say that there are points on the manifold, say the sphere, that there's that exhibit sign correlation? And my main point is that these two things are connected. And for people who like Berry's wave model, which I will describe, we'll connect that as well. And the main takeaway from this talk is as follows. For a generic manifold, you take a sphere and deform it a little in some direction. You'd expect that the eigenfunctions do not grow very much. You expect them to be basically constant in the sense that the L infinity norm is logarithmic. There's many reasons to believe this. The main takeaway from this talk is if this is not true, and most examples that we have are of this type, it's not true, you start getting interesting interactions with sign correlations. And I'll make all of it precise. Okay, so what do we actually know? What we know is we have a very beautiful, precise result about how much eigenfunctions can grow. So the setting here is with a nice complex manifold. If you want to just think about the one-dimensional torus and the two-dimensional torus, that's fine. The rest, I'll have examples that are on the one-dimensional torus and two-dimensional torus. If you want to think about the two-sphere, that's fine. You will not lose anything for the rest of the talk. The things I'm talking about here will be visible in one dimension. And I'll have pictures. But in general, so big of D is 1 or 2. But in general, there's a bound and it's polynomial and it's attained. So everybody's happy, right? You get a sharp bound. And it's attained in particular for the eigenfunctions of the sphere. So here's an example to give. There's a subsequence of eigenfunctions that's more and more concentrated at the north and south pole, and they attain this bound. Okay. And the sort of another way of thinking about this is, so this is the main ingredient that will be in many of the subsequent slides. if an eigenfunction is big somewhere, then the subsequent eigenfunctions will probably not be big there. And what we're thinking about it is exactly the local while log with a point x where one of those is very big. Now the sum is actually small, right? The sum is very constant. In particular, you can actually use this result because if you go from n to n plus 1, right, the difference in the sum between n and n plus 1 is roughly order 1. I mean, it's the error term, the maximum variation, and you plug in, you get with Weil's law exactly this question. Because you can think of this as a generalization of logisticity. Okay, so we have a wonderful growth bound, and it's sharp. So why am I here, right? Why am I saying anything at all? Well, the reason is, it seems to be a very exceptional case. As not so surprising mathematically, the sphere is special. The sphere is in some sense the extreme example. It exhibits a large amount of eigenfunction growth. If you take a generic manifold, again, think of a sphere and just do some C-infinity perturbation of the thing, right? Just put a little dent in it. I mean, as nice as you want, but any generic dent, you would expect that this does not happen anymore. You'd expect that this is very difficult. So somehow this type of growth rate seems to require a large amount of structure. And this is not clear. Is that me? We'll see. So this is sort of, this is the question mark that motivated me, right? How are these things connected? What is the underlying mechanism? Okay, I'll give you another example because it's very pretty. So let's take the d-dimensional torus. We'll see. D-dimensional torus. The eigenfunctions are just standard together. I'm here, it's not just me, right? Yeah. Okay, thank you. Yeah, weird kind of hallucinations to have on stage. Okay, so eigenfunctions, they're very nice, they're very explicit, and they're very beautiful. And now the question is, how big can such a thing be? It's a very, let's go away from the sphere and let's do some explicit computation. It turns out eigenfunctions are very nice because in the three-dimensional torus, they're just indexed by lattice points, and it's the distance of the lattice point to the origin that tells me about the eigenvalue. So if I fix a particular eigenvalue, and I'm trying to understand, what are the eigenfunctions at that scale? Well, the eigenvalue defines a sphere in Euclidean space, and the lattice points on the sphere index the eigenfunctions with that eigenvalue. And then you can combine them in any way you like. So how do we make such a thing big? And the answer is, well, it's actually just Cauchy-Schwarz. So there's a very easy bound, right? Because these things are all just 1 at most. And they're all 1 in the origin, right? If x is 0, they are 1. So we don't lose in the first step. And then we do Cauchy-Schwarz. This is actually just a 2 norm, which we always use to normalize. And the relevant question is, how big can this be? And this is just a very old question rephrased, right? It's the number of lattice points on a sphere. So this has been studied in number theory for a very long time. This is well known. And the easiest to state result is that if it's sufficiently high dimensions, which is 5, then this is very, very nicely uniform and you get this growth rate. So it used to be t minus 1 over 4 for the torus. Now it's t minus 2 over 4 for, t minus 1 over 4 for the sphere, t minus 2 over 4 for the torus. You see both of them have substantial amounts of eigenfunction growth, great polynomial in the eigenvalue. And of course, neither of them are generic. Both of them have tons and tons of structure. So what can you say about the generic case? So there is a result that says if you don't have conjugate points, so sort of ruling out north and south pole, you can gain a little. And there are other results of this flavor for certain kinds of manifolds, but the improvement seems to be generally logarithmic. So what people can do, sorry, it's number n. It's generally logarithmic. So what people can do is they can sort of rule out the extremal case and saying on a certain assumption, if the manifold does not behave like a sphere, things are at least a little bit better. But what you really expect is that for generic manifolds, this is not even polynomial, right? This is a very sort of pinpoint improvement. And what you really expect is something like lambda into the epsilon or even something better. So, the prediction, okay? And the prediction is, and I'm sorry if I tried very hard to find out sort of first set this various people came up with this. The generic, and I'm not defining it, and it's in italics for a reason because it's not rigorous. Generically, what you should expect is logarithmic growth, square root of a logarithm, which is very, very slow, which basically tells you that eigenfunctions and general manifolds should look a lot like sines and cosines, right? They don't concentrate too much. This is a very small quantity. And okay, here's some pictures to illustrate this. So this is sort of funny. This is where are the maxima located? So these people look at the couple of thousand eigenfunctions and they note the maxima, they draw them in different domains, sort of a pretty picture. But what they also did is they looked at how the maxima grow for these domains that you've just seen, and you see as the eigenvalue increases, the L infinity norm increases as well. But look at the scale, 2, 4, 6, right? And this is really hardly polynomial, right? Square root log makes sense to the extent that numerics can capture. Okay, so we have this very interesting conundrum. And the conundrum is we have beautiful endpoint results, and they're sharp on the sphere, and they're, they're a slight factor of the torus, and you can have highly concentrated eigenfunctions on the sphere, and you can have highly concentrated eigenfunctions on the torus, and everything's great. But on a general domain, if you draw one on the blackboard, you expect a square root of a log. That's a huge gap. And okay, so what I'm going to do is I'm going to introduce you to the random weight model, which is sort of a prediction of what eigenfunctions should actually look like. And it's a very pretty one. So basically, what you should think of as an eigenfunction generically, if you look at a small patch of the manifold and you see, what does it look like? This small region. It should be a random superposition of weights pointing in random directions with the right oscillation rate. So if you make an ansatz, then it should be cosine square root lambda, because if you differentiate the cosine twice, you get the lambda. So you should make an ansatz like this. So what you see is here, n is a very large number. It's a random superposition of waves pointing in random directions. You should pick the rest ones. So you have waves pointing in random directions. They're randomly shifted. You get random coefficients, and you add up a great many of those and normalize in the correct way that the probability theory goes to something enough to zero or infinity. Okay, I don't expect you to remember this or what this is a heuristic, but we'll use it later once. In particular, we can use it to estimate the maximum, right? Because what this says, I have a very good idea what an eigenfunction is. It's just a local bunch of weights. Okay, so if I take a small patch, how big is this thing? Roughly size 1. Some fluctuation, right? I take the next patch, roughly size 1. Next patch, roughly size 1. How many patches do I have? Well, I've roughly, a wavelength is lambda divided by 1/2. So if I want to decompose the manifold, I get patches of roughly this many patches. And so what I have is I have a whole bunch of random variables that are all roughly size 1 that I expect to behave roughly like a Gaussian. So the main question is, if I have a whole bunch of Gaussians, what's the maximum of all of them? That's one way to think about the maximum. So if you have m Gaussians that are sort of independent, and you can think of these eigenfunctions as sort of independent, of course, this is against the entire spirit, but it's heuristic. Well, you get squared log n. One way of thinking. It's e to minus x squared over 2, right? Square root 4. Okay. So far, so good. So what we have up to now, we have a wonderful, beautiful, sharp result. We have other structured manifolds, and you can construct many more. In fact, anything that I can write down where I can do computations is probably so nice that maybe there is some concentration. It's sort of a fun thing, right? Because if it's beautiful enough that I can do the computation, it means there's symmetries with special functions, which means probably there is some way that waves cancel out and everything is nice and have concentration. If I write on a generic manifold, I can't do any computation. Okay, and we also have some idea of what should actually happen. Okay. So here's the thing, it's funny because I get this question every time I teach linear algebra, and I never thought about it much, but then it suddenly became useful. So when you teach eigenvectors, right, they always say, which one do you pick? Right? The one that goes in that direction, the one that goes in that direction. And the answer is, well, it's not an eigenvector, right? It's an eigenspace. A negative eigenvector is also an eigenvector, right? See, am I confusing people by going too elementary here? I hope not. So same thing for eigenfunctions, right? We always write on the eigenfunction, we say, oh, it's sine kx and cosine kx, right? But I could actually say the eigenfunctions are like sine x and minus sine 2x and sine 3x and minus sine 4x. Like, why not, right? Minus an eigenfunction is an eigenfunction. It's an eigenspace. a one-dimensional line. So, I could take a random choice of signs, but if I just can I use this to get something out of this? Because one thing that's absolutely true is that for any choice of signs, any possible choice of signs, this is going to be a linear combination of eigenfunctions with an eigenfunction. These eigenfunctions are all orthogonal. I always get this integral identity. Usually this doesn't tell you very much, especially if you take all classes. But maybe, if you pick the signs in a funny way, maybe you can get something. The question is there a particularly smart choice of signs? And I claim that yes, there's at least one interesting choice of signs. So what would you want to do, right? So, suppose now you're trying to use an argument like this to explain that the next eigenfunction in the list, phi n plus 1, does not concentrate too much, it doesn't get too big. Well, how would you do it? Well, you want to sort of create problems, and how would you create problems? You create problems by saying, well, if phi n plus 1 is really big here, then I would want to make the signs in such a way that all the other things are also big there. And then I have two very big things that collide, right? That would be the idea. And we can exactly do this, right? So what we can actually do is we can flip the signs of the eigenfunction in such a way that it's positive to the point that I'm studying. I'm picking a point, I'm trying to use this statement to show that this cannot be too big in the point. And I pick the sign in such a way that, if it's positive, it stays positive. If it's negative, I flip it to be positive. Does this give us any? And I'm going to abbreviate this, and maybe it's a terrible choice of notation, but it's a little bit like an L1 spectrum projector, right? The L1 spectrum, the L2 spectrum projector is denoted by pi, so I just flip the pi, which happens to be a symbol in LaTeX. Maybe it's a terrible idea, but okay. We're stuck with this for the rest of the slides. Very simple. What you do is think of this is that the sum of the fifth and eigenfunctions, but the signs are flipped in such a way that in the point x, they're all positive. I can define this. And I claim it's a good linear combination to see what happens in the next one. So basic facts, this thing's not too big. It's just, I'll show you a couple of basic facts. None of them are very difficult. This just tells you that, you have basically n eigenfunctions, you do certain kind of sign combination. On average, this thing is size square root n. Square root constant. You can with some pointwise bounds. So on the diagonal, if you flip all the signs to be positive, you're actually looking at this. You're looking at the sum of absolute values. And you can bound this from above by n, the small error term. And you can bound it from below by a polynomial term. And both these are sharp. Okay? And what I believe is that the lower bound is probably not sharp on average. I think the lower bound can probably be improved. It's pointwise optimal, but question for the audience that I've never seen. The universal estimate for the sum of all one nodes. Like this shouldn't be too small somehow. I don't know. I thought I'd throw it up because maybe I get some fun comments. Maybe you only lose a log. Anyway, not the point. Not the point. So let's go back. Square root of a log. In the same sense of generically as above, I claim that if you do the following, if you pick a point x, how about I draw this? We pick a point x, and I have my first n eigenfunctions. And I look at this thing, and I flip all the signs of the eigenfunctions that are all positive here. So what do I expect the thing to be? Well, I expect it to be very, very large, right? Roughly size n. Maybe even a little bit larger, but roughly this, right? And these eigenfunctions are very nice, smooth, continuous functions. So what I would expect is that in a neighborhood, it's still roughly size n. And you can predict what that neighborhood is because it's roughly a wavelength. So this is roughly n to the minus 1 over d. And now, question for the audience, what do you expect the thing to be far away from this? Well, going back to what I've shown you initially, right, you expect the thing to be sort of random, right? Because you put random signs, or not random signs, you put deterministic signs depending on this point. But does the eigenfunction over here really care what happens over there? What you'd expect is these vectors to be big here. I think you expect it to sort of random fluctuations here. And those would be the scale of square root. This is what I'm predicting, and you can sort of see this generically to be true in the same sense as above. And I claim that these two things are not unconnected. In fact, they're quite connected. And whenever this is false, something very interesting happens because I'm flipping eigenfunctions here to all be terminated in sign. You'll have the same sign. And out here, far away, something happens that's not random. That's above a square root n. And I'll call that in analogy to quantum mechanics, I'll call it the spooky action at a distance, and I'll show you a picture in a second. So where's the spooky action at a distance coming from? So there's a letter. I think that's the origin of the phrase. That Einstein complaining to Born that quantum mechanics should not have spooky action at a distance. Everything should be sort of nice and local, right? And so here's my fun joke. I translated this myself, and I was very diligent, and I checked the dictionary for this word, which roughly means spooky. But the dictionary is giving an interesting analogous meaning. It says spectral, which I thought was very spooky. Maybe a good sign. Anyways, there's a spectral action at a distance. And well, I was tempted for a second to call it spectral action at a distance, but that would be so confusing. Hence the temptation. So let me show this, what this actually looks like. Easiest example, we're going to take the interval of length I, we're going to put 3 boundary conditions. This is the first example you look at. It's a one-dimensional manifold. And the eigenfunctions are completely explicit. Like this is high school trigonometry, sine kx. It's gorgeous. Now what I'm going to do is I'm going to flip all the first, because first 100 eigenfunctions. I'm going to flip the signs so they're all positive in 0.1. And then I'm going to plot this, what this looks like. And it looks like this. So they're all positive in 1. I'm okay with that. That's what I built them to do, right? And then this is not square root n. I mean, I'm having 500 points, right? Square root of 500 is what, 25, 20? Somewhere in the middle. So this should be 20, right? This is what I expect. This kind of fluctuation, right? Here is this. Here's another example. Here it is. I'm taking the square now. I'm looking at the first 675. That's 25 squared, I think, and that's because I don't want to have any bias. I'm taking the point 1.3, 1.3. Okay, and I'm sorting them all to be positive there. So you see that this point here, and then you still have an interesting interaction. Other examples: pi over 2, pi over 2. It doesn't look spooky, but if you see there's actually weird kind of rings that drop out, also spooky. Now, all the examples I've shown you are spooky. Why are they all spooky? Well, these are all examples of manifolds on which the eigenfunctions actually grow. Now, I expect some pushback on this on a one-dimensional manifold because signs do not grow. Signs are nicely bounded by 1. But more speaking, in more ways than one, the standard sign basis does actually grow, even though it doesn't. I'll have a slide on this. So the main theorem is actually if you have a manifold on which eigenfunctions can grow, then this actually enforces a kind of spooky correlation of this, informally put. So whenever you have growth of eigenfunctions, you will see something like this. And of course, the usual problem is, I've said this already, the ones we can study are the ones with closed form expressions. Closed form expressions allow for explicit computations. Explicit computations are possible because the algebra is nice, the structure is nice, and there might be wave cancellation, everything's great, which is not represented. It's tricky. Okay, so and it's a bit hard to sort of visualize the theorem. Like, it's very hard to get your hands on generic eigenfunctions, right? It's very hard to say what the typical case should be. But there's one very nice trick, which is you take a manifold like the sphere, which has very, very large eigenspaces. So if you look at a certain eigenspace, a certain eigenvalue, there's more than one solution to the equation. There's an entire eigenspace with a certain dimensionality. And then instead of taking the random base, the standard basis, you pick a random basis. Right? If you have a standard Euclidean space and you do random rotation, it's still a basis. So you can look at that. You can look at random linear combinations. Those could behave like generic eigenfunctions. So I'll give you an example. If you take the standard basis of eigenfunctions on the sphere, on S1, the circle, which is sines and cosines, then you do see spooky action at a distance, but they're structured. If you take a random basis, which is very simple, right? Because each eigenspace has multiplicity 2, there's sine kx and cosine kx, and you take a random rotation of that two-dimensional space. then you can actually prove, and it's not very difficult, that this does not happen. And this could be with a great deal of around. So I did it twice, one as a proof of concept, but this for the experience. Here's an example, right? So I'm taking the first 250 eigenfunctions on the circle. I'm sorting them all to be positive in one, just as I did before. And instead of any spooky spikes, just random white noise. And this is the kind of thing you would expect if there's no growth. This is the thing you'd expect generic. Is it 45 minutes plus 5 questions? Sounds good. So this is random noise. Here's another example, right? You fix them in a, oops, this should be pi. Sorry about that. You organize them to be in pi, but it's a random rotation, and you expect this to be white noise at the square root n scale. Here's another example. So this is one that's not usually considered. It's a quarter of a disk, Dirichlet boundary conditions, and it looks like sort of random waves, but then if you look carefully, there's a second spike here. So I think this one probably also has growth. Lots of examples one can do. There's lots of special function identities you could try to prove. I did not pursue them all. If you do Neumann boundary conditions, it's even more fun. You actually get a kind of ring. Again, all of this could be done. At some point you run out of special function energy. Okay, let me state the main result somewhat informally. And this is slightly less informally than before, still somewhat informally. Suppose you have a nice manifold, and suppose the next eigenfunction assumes its maximum in a certain point. Then you can bound this maximum. And you can, it looks a little bit complicated, I'll let me untangle this. This is the sum of the absolute value of the eigenfunction, the first n eigenfunctions in that point. This is an integral of the manifold, except you take out a ball centered at that point. So you remove this piece. You look at the rest only. And what you integrate over is the nice eigenfunction itself against this thing, which is essentially random, right? If there's no spooky action, this is some random here, size squared n. And what I'm claiming is that this inequality tells you a lot about how eigenfunction growth can happen, and why generically it doesn't happen faster than a logarithm. I claim that this inequality gives you exactly that. Because if it's large, right? If the eigenfunction would be large in that point C, then what has to happen, right? I mean, n you can't fix, right? And it's given this thing is either small, or this thing is large, or both. So these are the options that you have. And now it gets more fun. So it turns out the first case won't surprise you. The first case won't happen just out of nowhere. The first case you don't have to worry about. There's the following nice lemma that says that this term that you're interested in is not too small. It's roughly n divided by the maximum you've seen up to now. So if you have a nice generic manifold, and the first 500 eigenfunctions don't grow quickly, they're basically constant. This is roughly size 1, or it's up, maybe it's logarithmic. This is roughly size, it's exactly size n. This thing's roughly size n. So if you delocalize up to a certain point, if everything's very flat, there are no large maxima, this term is not a problem. In fact, this term, if you look at the equation, it cancels each act, right? It's the roughly size n. This is a constant. So the first term is not going to work against here. And so the inequality is also sharp. Which means once you have delocalized eigenfunctions, highly concentrated eigenfunctions, this term can also contribute, but in the beginning, it's only the second term that makes things big. It's the only one. So this is the only reason why things are big. Maybe I'll skip these slides. How about that? Okay. Maybe I don't need to talk about this. So last sort of takeaway message, okay, how big do we expect this integral to be, right? And I'm claiming it's the only reason why eigenfunctions grow. How big is it? Well, it depends on the eigenfunctions, and it's hard to say. It depends on the manifold. But you can go back to various random walk models and say, well, wait a second, I have a pretty good idea what an eigenfunction looks like, right? It's roughly Gaussian here, it's roughly Gaussian here, or Gaussian in size, random wave. So if you do the scaling, you expect this to be roughly a Gaussian random variable. And now if you tie it back in with the maximum of m Gaussian being roughly square root log m, you recover exactly the prediction that I had at the beginning of square root log. square log lambda. So what I like about this is previously we said it's square root log lambda because Berry's random wave model tells us there's independent Gaussian sized waves, which is a strong pointwise statement that's clearly false. Eigenfunctions are not pointwise independent, they're highly interconnected. This gives you the same connection, but it's under an integral sign, right? It's integrated out, so it's much nicer. It's a lot, it assumes less if you want. Okay, and I'm near the 45 minutes. So what am I not talking about? I'm not talking about special function identities, because all the examples of nice manifolds that we have, you can do computations. There is spooky action. There's interesting things happen with special functions. For example, if you take this entire thing and put it on the sphere, you run into, right? If you take a torus, you're going to get some funny connection about this sum being connected to this sum in a non-trivial negative correlation, and you can play with this. On S2, you get an interesting statement about Legendre polynomials that have an interesting behavior with respect to the next Legendre polynomial. And you can play this game on any manifold where there is eigenfunction growth, and you can compute the eigenfunctions. So what I'm telling you is the only way for eigenfunction growth to happen is for this integral to be large, which tells you there's an interesting connection between a suitable linear combination of the first n eigenfunction and the next one, which boils down to special function identities. Other thing, okay, we look at one particular sign flip, right? I pick a sign flip to be positive in one point, but there's many other sign flips, many others. And in fact, what you could do is you could take, you have n functions, you look at the bottom third in terms of size. So the 30% that are the smallest, and you just flip those signs randomly. That gives you an exponentially large number of functions that are orthogonal. And the previous results still sort of apply. So basically in the presence of eigenfunction growth, not only do you have a special function identity with respect to a special sign or connection, but there's actually an exponentially large number of families of this flavor that have an interesting connection to this, which gives you more special function identities. And of course, you can also think about the Gaussian free field in the background. Somehow this is there's an interesting global correlation that this. Okay, long story short, eigenfunctions says something interesting about the manifold. The manifold has to be very, very structured, but it's not really clear what that means. What's known is it can't be like a sphere. It's not really clear what's required after that. There's a very nice prediction from the sort of pointwise random wave model, which is numerically meaningful. And what I'm claiming is it's a lot of fun to look at linear combinations. They actually tell you something, and what you get is if you have group of eigenfunctions, then you have a global correlation of sign of eigenfunctions. And you can see this on the computer, and you can see it on the one-dimensional interval. And in particular, this recovers this estimate here, but in a stable, integrated sense, as opposed to a pointwise evaluation, which is not as robust. And you get special function identities. And somehow what you get is that the moment you have eigenfunction growth, you get a really funny phenomenon where 2 points on the manifold are very far away from each other, but the eigenfunctions in one point care greatly what the other one does. So look cute. And with this, I stop exactly on that. Yes, thank you.
Any questions or comments?
Thank you for a very interesting talk. So let me start with the comment. In fact, at least as far as the maximal growth of eigenfunctions, there is a well understood dynamical reason why this happens. Basically, you make a point as a feature that the point is measurement, that the growth from this point is coming back. Then the maximal growth. That was proved. So let me pull in this view.
Yes.
And this leads to the following question. So I'm wondering if your actually classical counter. So you can describe in the world quantum mechanics. Then you do have an idea what's happening to quantum.
I have absolutely no idea. I don't know. That's the short answer. I don't know.
But I think that should be somewhere.
Yes. No. I agree. I agree. Everything that I told you is in a certain sense extremely robust. I was actually amazed by this. I'm not very good at numerics, and even though I messed up the numerics, it still worked. And then I fixed the bug, and it still worked. It's a tremendously robust phenomenon of stuff. So yes, this would be very interesting.
You are floating in and out of Schrödinger, so I might not quote something, but let's say you take Anderson model and eigenfunctions. Would you be able to say that the signs are correlated or decorrelated?
I mean, in Anderson, I would expect it to be extremely decorrelated. And no, of course not, but and extremely decorrelated, and they would also be, they're not talking to right now. I see. Yeah. They don't talk to each other. Yeah. Right. One example. Possibly. I mean,
it's important.
I see. So I mean, I haven't talked about Schrödinger, but you're right. It floated in 1D Schrödinger, which was sort of unconnected. Like, honestly, the fact that I did this 1D Schrödinger, I think 8 years ago, I only realized after looking at this.
Yes, I probably should.
Everything.
Yeah,
well, it depends on scaling the model, but everything that I'm saying should hold true in some form for Schrödinger. I sort of believe this. But not all Schrödingers, but some assumptions. And yeah, Anderson, okay, I have no idea, but it's a great question.
It's important.
I have no idea what's important, but we shall.
One-dimensional thinking about getting polynomials is surprising that there's zero measure exceptions.
Yes.
It is known for one-dimensional problems, let's say, orthogonal polynomials with respect to something.
Right. So we looked at this a little bit, and it seems to be again a pretty robust phenomenon. So if you look at the paper, I think we did Legendre, we did Laguerre, maybe we did some Gegenbauer examples. So I would actually, I don't know what the full extent of the phenomenon is. I think it's tremendously interesting. The special function classes we looked at, because they're easy and explicit, and you just check, they worked. So our paper has examples for Laguerre, has examples for even, you can think of Laguerre as radial in higher dimensions, right? And there's examples there as well. And what I'm tempted to believe is that for fairly general Schrödinger operators, 1D, and nice potential, say C1 potential that goes up to infinity at a reasonable rate, at a great level of generality, you're going to see exactly this. You're going to see there's measure zero pairs that are correlated. And I expect it to be generic. I'm sure it's possible to build counter examples. We actually tried to build certain counter examples. What you would require for certain type of counter examples, you would require that WKP expansion does not work. And you would also require that the eigenvalues have a certain number theoretic structure of sort of being a certain progression, which you do get for Hermite, right? Like n plus 1/2 or something, n squared, n times n plus 1. So there is some structure there. But I think at a general level, like in a category sense, something like this, yes, I expect this phenomenon to occur. I don't think that Hermites are the exception. I think they're the rule. Yes, that would be very strong.
Is it like this last thing? Is it a one-dimensional thing, or is it?
I don't know. In higher dimensions, I don't know. In 1D, I believe it pretty strongly. I think it's the rule. I think it would be fantastic if this could be proven in any form. Higher dimensions, I wouldn't be surprised either way. Higher dimensions, I only really studied Laplacian eigenfunctions, where again, I expect Einstein to be right in the sense that there is no spooky action generically. There is no eigenfunction growth beyond the logarithm. I think these are the same things. Higher dimensional Schrödinger, that's a big universe. So I'm not going to make any claims, but maybe natural analogy would be Schrödinger in high dimensions also generally does not have spooky connections. But 1D, yes, because 1D is rigid. the wave that goes up has to come down. And 1D, left and right.
How does the distance for which the spooky action happens change as you shift the point of the line?
Well, I mean, it's scale. So it's completely non-local. It depends on if you do the torus example. It depends on certain closure properties of geodesics in the torus. So there's no obvious rule. Also, like when on manifolds, everything's scale 1. So spooky actions size 1. I've not, Also, the question is, is this spooky or is this spooky? What's your threshold? So there's maybe too many ways you can interpret the question. But they're far away. That's why it's far away. The size 1. They're comparable to the diameter away. Yeah, that one is actually no. This one's 3. Because I picked 1 and it happens to be 3 because if you take the geodesic with slope 3 on the 2-dimensional torus, it closes up in a certain asymmetric fashion. Yeah.
So this happens at every point of the line.
Actually, no. I'm not making any claims on this. If you have eigenfunction growth, this happens in the points where the maxima are assumed. Now, specific manifolds such as the 1-dimensional torus, you can ask whether this happens at any point, and it becomes a question about certain sign sum identities that one could try to pursue, but like each manifold where things are nice, like the sphere or the torus or even the 1-dimensional circle, there's certainly very interesting elementary identities floating around here, and there's slightly too many for me to sort of. If it was 1, I would have done it, but there's like 15, and at some point I'm like, can't do them all.
Thank you. Is there something like
in a certain sense, yes. What happens is generically, if you flip the signs, and the pick a point, flip the signs always be positive. What you expect is you expect it to be size n, and you expect it to be a bump, and the scale of the bump should be exactly the one predicted by the other. In that sense.
Yeah, so now I know. But there is an article by Einstein's prediction and Heisenberg for how it's related and how it talks about download policy. So it's kind of.
I mean, maybe I shouldn't claim too much connection to Einstein. I'm not sure it can be one-to-one. It fits so well. I couldn't resist. I'm not claiming to be doing physics, but I don't know. So maybe it's more similar than I expect. No, for sure. I mean, certain principles that sort of follow from a good understanding of eigenfunctions will give you answers. That's right. Right, so the question is if I randomly rotate the eigenfunctions, I don't see spooky action. Right, I don't. It goes away immediately. So it becomes difficult, right? So here's the reason why it's difficult. On manifolds, where you have big eigenspaces, large multiplicity of the eigenvalue, you already have tons and tons of structure, you're already non-generic. So this is a trick to produce generic examples from the little thing that we can compute. It's hard to see anything definite. The interesting question in this direction is, you take the sphere and you take random linear combinations of the spherical harmonics and you produce a basis that is very, very constant. Such that the eigenfunctions are never large. And this is sort of a famous open problem. But the square root log has been produced in the 90s. So log squared.
Other questions? Tomorrow there will be Portland residents from the 2-room second floor of this building. And probably say consulting the last moment from the different learning that extra property for the first lecture that 10. And then we also have a lunch and dinner plan tomorrow. So if you haven't got my mail, if you plan to join us, let me know. Tomorrow for lunch. So you're
So I have also a kind of curriculum. So what the little town on the Laplace would prefer this one much more. They already set the one out. No, but it's sort of like we present the one. I tried to be very simple points. I have to be so him on that. I tried so hard. Sort of prevent the result of following eigenfunctions and then decide to wonder what the point by square was.
But they didn't have to follow.